Last year, my brother and I released a video of our homemade CNC milling machine that we built from scratch, literally using playground pebbles and epoxy over a steel frame that we designed. Today, we want to add a DIY CNC lathe to our shop, and spoiler alert, we now have this beast in our garage. Since building the frame of our DIY CNC mill was over $8,000, I'm considering starting this project by borrowing a frame from a properly engineered machine and going on from there. Speaking of which, I'm noticing that small lathes are very expensive, likely because they are desirable, if not by industry, then probably by hobbyists as well. But the older and much better industrial machines seem to be obsolete. Here's proof. When I go looking around, I find machines like this Haas for free as long as I pay to remove it. This one is in very bad shape, so I'm going to pass. Well, the next contender is a $250,000 German lathe from 1994 selling for $1,500.
So we arranged to meet the owners at their warehouse, and well, here we are.
We're on camera. We are on camera. Thanks for letting me film this. No problem. So where's this lathe?
Well, the lathe was buried in the back, all covered in dirt, but I did like it at first sight. Right away it looks very heavy duty, but we've got some damage here and there, like this crack on the window. The door slides really well still, and immediately inside we can see this heavy duty tailstock, the tool turret, and our A26 spindle. Then over here we've got the actual control panel, which still has the original keys. So let's turn those and see if the machine will power up. Oh, whoa! Subscribe? Must have been the last thing Adam did before shutting this down. Looking down below, we have a bin where finished parts roll into. I wonder if there's anything still in there.
Got it!
So now that we're satisfied with what we see, let's give Adam his money and get to work. The first few minutes were spent on clearing the room so I have space to work, since I do plan on taking this machine apart piece by piece down to the nuts and bolts. When we were done, I was super excited to begin. But first, Adam helped me demonstrate to all of you that this is not a small machine. Pretty big. Alright, so let's pull out the work clothes and start cleaning this machine. Water alone seems to be working well, but this is definitely taking way longer than I'd like it to. At least now the machine is clean not only on the outside but the inside as well, which means that I can work comfortably. Now, I shift my focus to taking off the sliding door just to learn that it's extremely heavy. I then got down on my knees and started clearing off the 30-year-old metal shavings, which to no surprise got absolutely everywhere. Next, let's take off the main electrical cabinet, but leave all of the electronics inside for now. So I navigated Adam with the mobile lift until we got it properly lined up underneath. We then strapped this cabinet for safety because it's super heavy, and then we slowly rolled it out of the way. Now that the panels are off the lathe and the wires are managed, let's shift our focus to the spindle assembly. Right here is our spindle itself, and you can see that it connects through these belts to this massive 30 horsepower servo, so let's get started and take this beast of a motor off. We start by disconnecting the electrical wires, loosening the mounting bolts, and then using the lift again to pull on a ratchet strap that we attached. And voila! There leaves another 300 pounds. Moving this machine all by myself is beginning to seem possible. Let's shift our attention to the front, where I remove another cover plate, and of course I find this again. So make sure to subscribe because we have giveaways in every video, such as a unit of our Injecto, which is a desktop plastic injection machine, or Shreddy, our desktop shredder. Today we're giving away a Shreddy to 4 lucky subscribers, so be sure to subscribe and sign up for the giveaway. You can find the giveaway link in the description. Perfect, so now we're at the main control panel where we plan on recycling all of the old technology. Why? Because we're installing our own modern controller for the machine in place of these buttons and screen. This leaves us with the final important piece to remove, which is the rotating control box, which also means that we now have to take all of these panels outside and move on to the very dirty next step of washing them from their 28 years of coolant and grease buildup. The first step is to run inside and get the owner's power washer, which they kindly offered to let me use. Now the coolant is soluble in water, so it cleaned off very nicely, but despite that, this was the most powerful power washer that I've ever used, which made the job super easy and fun. Back to the machine, let's fast forward through the boring part, where we remove some spindle covers, other panels, as well as the weight covers, which exposed this huge pile of metal chips that got trapped below them. Anyways, we cleaned those and continued to remove a few more panels here and there, which left me exhausted. With the base exposed, I grabbed a wire brush and cleaned the machine super well for the next hour. I tried to get as much dirt off as possible because it's way easier to clean the floors here than it is back home.
Alright, so there's the core of our turning center and it looks beautiful. We got the 3 main components, the tailstock,
the tool turret, and then of course our spindle. Now the fourth and last component would be the base itself, which I was expecting to be a cast iron base. But when I took a closer look, I noticed that this is not cast iron, but it actually looks to be welded steel sheet. What's more interesting than that is that we have these hatches on the back of it, which leads me to believe that this is actually full of sand. Now this is great because originally I planned for about $2,000 in rigging fees, and it doesn't look like I'm going to incur that expense anymore because I can probably get away with just a Harbor Freight trailer. So let's open up those hatches and see what's actually inside.
Opening these up takes just an Allen key, so seconds later we got the lids off and... Oh my god, there's actually sand inside this machine. This is so unusual, which makes me so super lucky. I immediately grabbed an empty shop vac and started draining the sand out of the frame. But I had nowhere to store it, so I quickly ran to Home Depot to get some buckets, but as I reached out for them I realized, wait a second, if I'm spending money on a container, I might as well use something that I need at home, like these 17-gallon totes that I use for storage. These worked great and held several loads of sand in each tote, so I kept draining the sand for a while using this method because it worked really efficiently.
So we managed to get about 99% of the sand out, which is fine because the point is not to clean this up, it's just to make this substantially lighter. We also did the same to the bottom. We're not quite done, but we got a lot of sand being removed and taken home.
In fact, we managed to fill 10 of these totes, each weighing close to 185 pounds for a total of 1,850 pounds. In our DIY CNC machine video, I talk about the science behind making the machine heavier in order to reduce vibrations. They decided to use sand to achieve this, which is not optimal but definitely works. Okay, so with the sand out, we want to take the top frame half off the bottom part. Now the first thing I want to do is actually pull off these three components from the top part in order to make it lighter. So I see a spot for some eye bolts right over here that I can use to lift this out. I also see place for eye bolts on this turret over here, and well, I couldn't find any places for eye bolts on the tailstock, but I can just hook or strap it somehow. Having removed so much weight, we assume that we can finish the rest of the job with just a shop crane, so we picked one up at Harbor Freight. This thing is super heavy to lift alone, so I recommend you get some help. I also took it apart into as many pieces as possible for transportation and to make it easier on my back. And luckily, reassembling these doesn't take more than a minute with these quick connect parts that are included with all modern shop cranes. You just put the legs back in place and slide these bolts in. At this point, we're ready to roll it in and start lifting parts off. Or so I thought. Turns out we had to remove the chip conveyor to slide the legs of the crane under the lathe. But that was a piece of cake with Adam's forklift.
Now many of you are likely wondering, why didn't I just disassemble the lathe with the forklift? And the answer is simple. I want to disassemble it in the same way I plan to reassemble it, aka with the shop crane. Otherwise I will have no guarantee that I can rebuild this at home.
Moving on, the crane fit nicely, so we attached the eye bolts onto the spindle block, attached the crane to it for safety, and then loosened the 4 bolts holding it in place. Well, we started cranking on the crane and it lifted the spindle assembly as expected. So we're ready to take that out and move on to the tool turret, which we also had no issues with, although it was surprisingly much heavier than the spindle assembly. And lastly, we have this janky strapping contraption for the tailstock, but it worked and we got it out. The years of oil buildup below it though was rather nasty, so we took a second to clean this all up with SEP so that we don't bring it back home with us. I also decided to remove the servo motor as well as the ball screw setup for the tool turret just to reduce weight from the heaviest piece of this project, because I wasn't sure if the crane could even lift it. But to my surprise, after attaching chains around the top half of the frame and rolling the crane in, it worked like magic. However, this thing is heavy. I can feel it when I'm cranking down on the hydraulic jack. So it's important not to forget to adjust the weight setting on the extension, which we did. I was super relieved to pull this piece back and lower it to the ground. I actually managed to lift the heaviest component in the project, which means that I should have no issues moving this by myself. Alright, so the last piece we're going to take off is the hydraulic tank. You can see I've already started sucking out some of the oil inside using this. Speaking of oil, check out this buildup of grease on here. It's super gross. But I did manage to find a very, presumably, old Allen wrench that I'm going to keep. I guess this deal paid off already. Since I'm still waiting for the hydraulic tank to drain, I'm back here with the ZEP cleaning away in preparation for the move. Now, back to the hydraulic oil. I managed to suck out not just one 5-gallon bucket of this stuff, but 2.5 buckets, and this stuff isn't exactly cheap. We used the crane to remove the pump as well, which leaves us with the absolute final part, the base of the lathe. This was made of thinner steel than the top half, so it wasn't as heavy. I easily loaded all of these onto a Home Depot flatbed rental truck and brought them into my brand new garage. I unloaded the crane first, which is a real pain to lift and unload by myself over and over again. but after assembling it, the rest of the job was really simple. I'm just working backwards here to unload all my parts from the truck, and now I'm heading off for the long drive back to Adams to come back with the second and final load. Now that I'm back, the same pattern of hard work continues. Plus it's nighttime, so I'm in a rush to get back to Home Depot with the truck because they charge me by the minute. But while there, I need to pick some new colors for our new lathe, so what better choice than the Action Box colors themselves? Now, I'm no expert at painting, but I was told that most metal colors will work, so I got a urethane-based enamel since it washes easily and doesn't smell. Painting didn't take too long and was a nice break from the labor-intensive work. We tried to paint the moving parts in orange and the stationary panels in black. Not just for the looks, but also to have a visual cue for what areas to watch out for when the machine is running. We then completed painting all the panels and let the paint cure overnight. I'm no artist, so hopefully this turns out looking good. And on that note, we can now begin to work backwards to reassemble the lathe. Luckily, this was very simple to do on my own using the engine crane, and within just a few minutes, I got the top piece in. So far, in my opinion, it's looking really good. I'm really happy with how this is turning out. So to continue working backwards, let's bring back the spindle, the turret, and last and most likely least, as I don't have much use for it, the tailstock.
Alright, as you can see, before bringing on the next part, I painted the machine black and I also painted the highlights in orange. So let's bring that tool turret over and keep going.
We'll put the 3 critical parts back on the frame for now without aligning them, but we will go over this process called tramming later. I almost forgot to install the ball screw into the tool turret, so I'll do that now quickly before reinstalling the tailstock. I'll also give it a quick test here just to confirm, as I did, that everything works good. Last and least, as promised, I brought over the tailstock and remounted it with the 4 large bolts. I genuinely can't believe that this machine is in my garage. It looks so cool and is far higher quality than anything we could have fabricated at home. Goal number 1, let's eliminate all hydraulics and make this 100% electric. Let's go. Ooh, but before we start with those fun steps, let's just wrap up the frame by filling it up with all the sand that we pulled out of it. This is way easier than sucking it out with a vacuum and took no more than maybe 10 minutes. The trick is to pour the sand in, then push it backwards, and then repeat until we're all done. The last step is to close the hatch with the same covers that we took off and then put some caulking around it because it's going to be under a lot of vibrations and we want to make sure that the sand doesn't leak out. We do the same for all other covers, and after all 8, we're left with the original super heavy base.
Alright, so step 1 is done. And that was get a machine base so we don't have to reinvent the wheel as we did in our DIY CNC machine video. Now many people would suggest that this is simply a retrofit, and I can't argue with that. The true novelty in our machine is not the base, but rather in our solutions to replace the hydraulics with electromechanical equivalents to make this a more suitable machine for a home shop.
This massive hydraulic actuator is the first to go. It's used to open and close the chuck and is very heavy. This leaves us with a perfectly spinning spindle, which means I'm ready to install a spindle motor. I'm going to recycle this 2.3 kilowatt servo that we pulled out of our DIY plastic injection machine to prove that this can be done with standard home garage power. This will replace the original 30 horsepower motor. To understand whether our motor would work or not, I use a lathe torque calculator online, which confirms that this motor will work for the diameter and materials that I will likely be using. Mounting this motor took just an angle bracket, a drill, a tap, and this custom mounting plate. I marked the holes before drilling and tapping by hand, which worked out perfectly for our custom motor mount. Installing the motor is trivial with 4 screws, which leaves us with the pulley. I found this standard online, which I've never seen before, but it was very easy to install. I bought the appropriate belts from McMaster, slipped them on, and tensioned them. Finally, I connect the motor to the driver, and voila! It looks like we may have potential. Great! With the spindle spinning, we shift our attention to the next 2 motors. One to move the tools left and right, and the other to move them up and down. We'll get to the tool changer at the end. For reference, these are the original motors from this lathe, and these are the small 110-volt substitutes that I chose. I've recycled the same pulley from the original motor, but the mounting plate was far too different. Thanks to our DIY CNC mill, I made new custom plates in minutes which fit perfectly. And from there, everything moved smoothly. Literally, check this out. I'm getting super excited. Clearly, our Z-axis works and our spindle is also functional in both directions. This means we can repeat the same process for the X-axis. When I took the X-axis apart, the weight of the tool turret pulled itself all the way down. Using the same 110 volt motor and custom mounting plate, I managed to gain full control over the X-axis as well. Alright, so we've added motors to both of our axes as well as our spindle motor. And next we want to mechanize this over here so that we can electronically control our tailstock. Need to figure out a way to actually get this turret to turn and lock in place. And then we need a chuck clamp for our spindle.
Now, I want to test this machine before we continue to invest both time and money into developing these 3 items that I just told you about. In order to do that, I'm going to need a working chuck. And since this draw tube is not functional yet, I went ahead and bought this manual 5C collet chuck from eBay, and I've already installed the sacrificial plate on the spindle, as you can see. Now, I need to trim this in with the machine itself so that this chuck would fit on there. In order to do that, I need a controller for this machine.
Well, this controller just arrived in the mail from Masso, so let's crack it open and see what's inside. Looks promising. Let's also open up the pendant I bought. Now this is not our first rodeo with Masso. If you've been keeping up with our channel, you may have noticed that we use the exact same controller for our DIY CNC mill and a very similar controller for our DIY CNC router. This controller over here is absolutely amazing when it comes to hobby use. However, it is quite expensive. I think it was about $1,200. I'll put the actual number right up here. And then this pendant, which is a really nice to have, is about $150, I think. This is an all-in-one controller, and we're going to crack this open right now where I'm going to show you the actual controller itself, as well as how to make all the connections. And the last thing as promised is the pendant, and this is definitely a nice to have. You don't have to have this. It is quite expensive, but it does make the job a little easier if you're going to be using this machine every day. So I've got the controller mounted in a very janky way on a broomstick, and I'm doing that just until I can get all these panels installed again. In the meantime, we still need to connect this controller in here to those motor drivers. Wiring is simple because this controller is labeled very clearly and has extensive online documentation that walked me step by step. With the wiring done, we can close Masso and fire it up. 10 seconds later, we have a functional CNC lathe. To show you how this works, I'll start by pulling this super heavy tailstock out of the way so that we don't crash our turret into it. And here we go. The controller is outputting a pulse train, or a bunch of pulses, which are picked up by the motor drivers and converted to this accurate and smooth motion. But the issue is that the axes don't move the same distance that the controller is telling them to move. To prove this, I'll use a dial indicator and ask the machine to move 1 mm, 2 mm, 3 mm, 4 mm. As you can see, it's only moving about half that. At the end, we should be getting 10 mm of movement, but only got 5. To fix this really fast, I just go to the axis settings in the controller, find the parameter for number of steps to output per millimeter, and double them. Now I'm getting what I'm expecting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'll repeat for the x-axis.
Alright, everything is working as it should. The spindle is spinning, the z-axis is moving as it should, the x-axis is also functioning. Now I'm ready to put a tool into the tool turret and try to trim in this adapter plate for the manual chuck, which is going to enable us to use this lathe as a normal lathe. If everything works, we can continue with the hop-ups for the tailstock, where we're going to mechanize it. We're also going to mechanize the hydraulic chuck clamp on the spindle. And the most exciting part, we're going to have to try and figure out a way to get the actual automatic tool changer behind me to work as it should. Let's get to it.
I started by looking around machine auctions for the correct tool holders and won a super cheap lot that included a bunch of various lathe chucks, but also a bunch of these VDI 30 tool holders, which are the exact standard used by my lathe. Obviously, I got lucky yet again with this find, but it's all a part of the game. Try and you will succeed. When I grabbed 2 of these tool holders, it's evident that these are very greasy and likely haven't ever been cleaned. When I rub them, I can see a layer of clean bare metal below, so let's head over to the ultrasonic cleaner to make them brand new again. The process is very easy. I fill up the tub with my solvent of choice, which in this case is isopropyl. I place the parts in the tub and the grease dissolves right off. IPA is a great solvent for this application, but note that this is a dangerous practice as IPA is flammable. Since ultrasonic cleaners generate heat during operation, the risk of ignition is high. I like the results, so I'm going to wash all my parts now. When done, you can see that these look almost brand new. This VDI 30 standard is extremely easy to use. Just open up a single bolt, insert the tool holder, and the cam system will pull it in and lock it in place very repeatably and quickly. That's it! I now have room for 12 different tools on our Action Box lathe. I also purchased some carbide insert tooling, which are becoming very affordable thanks to some impressive modern powder technologies. They press the carbide powder into shape, one piece every few seconds, and then sinter them in a vacuum furnace, which by the way, I'm currently also building, so subscribe and turn on your bell to see that video. We have to face the cutters downwards since they are on the other side of the spindle, and we want to keep the conventional rotation direction. I also noticed from the side that our tool axis is not aligned to our x-axis rails, so let's loosen the turret plate and tune this. This piece is extremely heavy, which mandates the use of the trusty engine crane. I'm going to strap this prior to loosening bolts just as added safety. To rotate this upwards, I first loosened all the bolts on the face of the turret, and then I came up with the great idea of installing a tool holder, grabbing the longest steel rod I could find, and realizing I could have succeeded with much shorter.
So this here is how we align the tool angle to the x-axis rails. Once we get it to the correct angle, we just tighten those 8 bolts and it's gonna be rock solid.
But first, I'll remove the turret as I'm already here and test the through tool coolant mechanism, which I only just realized exists on this lathe. I'll use air instead of coolant. Well, it works. A straight-on view reveals the 12 holes used to feed coolant for each tool. Each of these holes had an O-ring and all O-rings were damaged, so I purchased new ones and replaced them. It'll be sweet if this actually works. So I put the turret head back on the lathe, tightened 4 of the bolts lightly, and used my long DIY lever arm to adjust the angle. I kept adjusting it until I got to the point where over 5 centimeters of travel, I only had 10 microns of drift. I also wanted to check the runout or wobble in the rotation of the turret to make sure it spins true. But to rotate it, I had no choice but to open up the back of the turret and start tinkering with what I believed would be the most difficult part of this project, the automated tool changer. With the cover open, I head over to the back and start guessing what's going on. I can tell we have some sort of a motor over here. I can also see we have a solenoid actuator here, likely to lock the tool in place, and down over here we have an encoder which likely gives us the tool position so we know which tool is currently selected. Removing these screws reveals an automated stepper motor, so let's replace that. But it does rotate a spring-loaded handle which I played with until this happened.
It clicked. Oh, there we go. Turret's moving. Alright, let's get another angle of this.
So here's what I've learned so far. We have this shaft that turns the turret. I can also turn it backwards, but it never seems to lock back again. To lock it, I need to actuate this electric solenoid, which I'm doing here mechanically. And while it's actuated, I turn the handle backwards until it clicks again, which locks the tools in place. Alright, let's keep gutting out the tool changer. This here is our absolute encoder. Basically, it knows exactly where it is at all times, even on startup before you rotate it, which is valuable because then the machine knows exactly which tool is selected right away. But let's gut that out because I know that for this project, instead of using this absolute encoder, I prefer to use a cheap incremental encoder because they cost just a few bucks and are much easier to replace in the future. They're also much easier to program, and with proper coding, it'll work just the same. You can see that these are different sizes, so I 3D printed an adapter, and now that I try it, it's actually a perfect fit. I'll quickly install it and we can get back to what we were doing. I spun the turret by hand first though to make sure that the encoder is coupled properly, as you can see. Now, back to the reason we opened this all up. I wanted to confirm that the turret spins true, and indeed there's only a 20 micron runout over a 20 centimeter diameter, so I'm not worried about that at all. With the turret perfectly lined up with the lathe, I'm starting to think about mechanizing this rotation, and that's when I noticed the shaft pops right out. So of course, I walk it over to the saw. Whoops, that's the ultra high vacuum video coming out next week. But on the left here, we can place our part in the vise and then bring over our electric Milwaukee saw. 10 seconds later, we're left with a small stub that I can attach our stepper motor to. For a mount, I just measured the hole distances and then 3D printed a mounting plate. This plate is a perfect fit, so I mounted on the motor and then installed a complete assembly. That looks and feels awesome, so it's time to make it work. I buy an Arduino microcontroller and get to programming on the Arduino IDE. In simple terms, here's the logic that I program. We start at the Maso controller where I'm going to select T11 M6, which is simple G code for change tool to tool 11.
Now you'll notice when I press run that the turret begins to turn, but you'll notice at first it does one full rotation. It does this only on startup to find the 0 position of the encoder. Once it finds the 0 position, it's going to start counting pulses, and there are 600 pulses per rotation. So I took these 600 pulses and split them into the 12 regions we have, which represent our 12 tools, and now we have these values associated with each tool. Whenever the encoder spits out these numbers into the Arduino that governs it, which we just programmed and have left back here, the Arduino is then going to know exactly which tool is presented in front of our spindle, and the Arduino is then going to output a 4-bit piece of data to our Maso controller, which can be read right here. Whenever the Maso controller reads the correct tool, it knows that it can begin the locking sequence, which then tightens our tool down and allows us to continue machining. So let me show you how this data is read dynamically by just changing to, say, tool 7, M6. You can see the turret begins to turn, and these values are changing live on screen. Once we get to the 4-bit data, which correlates to tool 7, it's going to lock the turret.
The last item left to wrap up the turret is this 3D printed housing that will replace this original cover.
Alrighty, so I've got my cover, I've got my screwdriver, so let's pack everything in here and close this up.
Okay, this next part is off script, but I just had to film it. I love when I design something and it works out perfectly. See this gap between this steel block and this plastic cover? It's crazy how close they get, but they don't actually touch. You know what they say, clearance is clearance. One other quick note on the 3D printed cover. I know a lot of people are gonna say it's not ideal, it's plastic. I think it's pretty cool that I was able to make it at home, and I would definitely recommend using plastic 3D prints wherever you can. There's no way I would have gone the original cover on here otherwise, so it is my best option and I'm gonna stick with it.
So back to installing our manual chuck. From the store, the chuck doesn't fit because the mounting plate needs to be machined after it's mounted so that it's perfectly squared to the lathe. I have a tool sticking way out because the turret travel is limited, and even though this is not ideal, I currently have no choice and will fix it later. But on the bright side, the chuck fits perfectly, so let's tighten it and start testing concentricity. The deviation is just microns, which is superb for my needs. So lucky me, let's move on and finally, after all this time, take our first cut. I installed a collet into the chuck and I just can't get over how awesome this looks. Anyways, I put this 1-inch rod from Shreddy, our DIY desktop shredder, into the chuck and I'm ready to surface it. For a first cut, that looks pretty good. I think I'm ready to program a CNC path in here. Although first, I do want to mention quickly that I did tram and align all of the lathe components, such as the spindle block and tailstock, so that everything is as squared away as possible.
While I've decided to omit this footage from the video, this is easy to do with a dial indicator, and better yet, check this out.
I got this super cool Hamer Centro probe that is installed into the spindle and helps you perfectly center your cutting tools to the chuck. It's an absolute must-have for any lathe owner.
Now, many people in the comments ask me, how can I afford all this stuff? And while I do have a full-time job as an R&D engineer, I don't use my personal income for any of this. I have sponsors willing to pay thousands of dollars for just 30 seconds of advertisement time in my YouTube videos. So if you post anything on Instagram or YouTube, just find someone who's willing to pay you for it. Similarly, if you have a product idea or if you already run a business and you're looking for someone like myself to expose it to millions of viewers, I have a solution for you. Just use Bix.
Making my profile on Bix took a minute, and it's been super helpful in finding businesses to sponsor my projects. And if you have a business, you can search for influencers on Bix who will promote your products on social media. It's honestly super simple. Make sure to check out Bix.co.
It's been 2 years since my brother Alan and I embarked on our own project to develop a home DIY CNC machine shop. We first posted the video of our DIY CNC Mill. We then posted our DIY CNC Router. We had a desktop plastic injection machine, and soon we have a metal 3D printer coming out. It's very unique, so make sure to subscribe. And to finalize that dream, we have the DIY CNC lathe right behind me, and I've genuinely not ran any parts on it. These are going to be the first. So to test the CNC capabilities of it, I've got some rods from Injecto, our desktop plastic injection machine, and I've also manually written some G-code, which we're gonna test right now. So let's push it into Masso and see how this machine performs.
Now I'm practically done. I can use this lathe as is, but I think it'll be pretty cool to automate that last component as I promised you. Here's my plan.
First, let's remove this manual collet chuck as well as its adapter plate. It's a really perfect fit, so it was a struggle to get off, but as always, when force doesn't work, just use more force.
So this is our actual raw A26 spindle.
This spindle accommodates any A26 chuck, like this one that I got in my auction lot. The added benefit of this is that I can use much bigger 20C collets compared to these 5C counterparts, which is nice if I ever want to machine bigger parts. These bolt right on with 6 screws. Now, this spins, but regardless, it's always a good idea to check concentricity to make sure that no dust or particles got jammed between the chuck and the spindle. My readings come out to just a few microns per rotation, so I'm gonna call this perfect. Okay, so we have these huge collets that fit right in here, but we need to somehow pull them backwards in order for them to close. To do that, I use a draw tube, which is just a pipe with threads on the end.
I insert it on the back and thread it onto the collet. This is where the magic happens. I need to invent an electronic method to pull this tube while allowing it to spin at 2000 RPM. Easy task, I guess?
Well, I made a quick prototype and sent it to my 3D printer to confirm. These truly are great tools if you're doing the type of stuff I'm doing. The first part is already mounted onto the spindle block, and to the second part here, I've installed a metal ring which I will now slide into place. With this random screwdriver, I'm also going to pin the two parts together, which leaves me with just 2 more components. The first is a thrust bearing, which is made up of many roller needles. This transfers force while one component is stationary and the other one is spinning. The last part is an M60 nut. I had to find all of these random components that would come together and perform my desired task. So here's how it works. Note that the metal ring pivots on the axis of the 2 bolts, which allows it to always stay perpendicular to the draw tube. It mates with the thrust bearing, which can then spin while applying all of the force to the spinning draw tube, effectively clamping the collet closed while the spindle is spinning. To actually actuate this back and forth, I need to order a linear actuator for over here. But I wanted to finish this final task in the lathe project prior to putting all of the cover panels back on the Action Box lathe. However, a few hours ago I purchased another CNC milling machine that will go right here. Even though that's great news, it means that the lathe has to be completed and all the panels have to be installed, as I don't have more room to store them. I actually used this same video that I made to work backwards when reinstalling the panels, and while it was easier to remove them than it was to put them back together, I eventually managed. Now, this machine is an absolute beauty, but speaking of beautiful, I had to call the boss over to help me as I needed some real muscle lifting this heavy door. So thanks a lot, boss. My next project here is to replace the shattered window. Here's what I found out so far. So this here is a polymer, likely polycarbonate, which is sandwiched between 2 pieces of glass, and this is how they actually make bulletproof glass. So it's a pretty good design for a machine that needs a window, but also provides some safety in case our workpiece goes flying out. So the best alternative is to cut a 1/2-inch sheet of polycarbonate into a new window. It's definitely much clearer, plus my little spindle motor isn't likely capable of swinging an object with sufficient inertia to pierce this. I guess if I ever learn otherwise, it'll be the hard way. Now I'm heading back to Adam's shop for the chip conveyor. I tried to grind it because I just need to use the bottom as a tub, but this was really difficult. Lucky for me, these sellers are super cool. Ready? Well, I brought what's left over home and cut it to my liking. I also picked one of the excess panels to use as a wall in the tub by blocking the open side and TIG welding it. This made my coolant tank watertight.
The next morning, the mill arrived, and check out my garage now. This is really crazy. I made sure my floor is rated to support this, which means we can now get back to our electronic chuck clamp. I made a slight redesign that had a load cell and a spring to buffer the vibrations, and then I cut all the parts on a plasma cutter. Ultimately, they assembled like a puzzle, and here's the result. I've gone ahead and welded all of our puzzle pieces and then installed them onto the lathe. I also went ahead and installed the linear actuator as well as the load cell, and in between here, as you saw in the CAD designs, we have the die spring. Now the point of the die spring is to buffer any oscillations that may be inherent within this design. Whatever force this linear actuator applies onto this load cell is directly proportional to the force that we therefore pull our draw tube with. The last step is to go write a program on Arduino which will allow us to modulate the amount of force that we apply onto our draw tube with the linear actuator. While we run the Arduino code, let's allow the 3D printers to run and make the electronic panels. Finishing the electronics is going to be really simple because we already had everything connected and we saw the machine work. So I know that these are all the components I'm going to need, and there's a ton of extra space within the original control box. This should be a really quick and trivial job, so I'll be back when we're done. Guys, how cool is this? We are done with the lathe. Let me show you what we've implemented over here, and then we can start making chips. We mounted the 3D printed panels we made not just for aesthetic reasons, but also to support the electronics of our draw tube mechanism. Let me show you how that works. First, we turn the machine on over here, and immediately both our systems come up, the Masso to control the machine and our draw tube controller. Let me show you the actual user interface that I programmed in here. First of all, we have a set value controlled by this encoder over here. When I turn it, you'll see the actual value down below immediately increase, and those are values read by our load cell, which means that our linear actuator is activated. You'll also notice that the actual value is always a little bit higher than the set value, which is fine for me because this is not meant to be an accurate system as much as it is meant to allow me to just go up and down in values as I need. So now, seeing that everything works, we are ready to go ahead and start making chips. There we have it, a custom chess piece on our Action Box lathe. If you enjoyed this video, please hit that subscribe button and give us a like. See you next time, folks.